I'm going to present our work, Rubiks, which is a practical 360-degree video streaming system for smartphones. This is a collaborative work with Huawei. So recently, 360-degree video streaming has been one of the most popular applications in VR community. So at first, let's take a look at what existing 360-degree video streaming systems look like. So this figure shows the architecture of the existing systems. Basically, the video server transmits 360-degree video data to the client who uses a mobile VR headset to watch the video. And the received video data is displayed on the screen of the smartphone. It is easily to find two major challenges in these kind of systems. The first one is decoding 360-degree videos on smartphone is slow because of the limited computational resources. Secondly, because of the limited size of the field of view, the user will only watch a small portion of the video, such that if you send the entire video to the client, then you will waste a lot of bandwidth. Recently, there have been works proposing to use tile-based streaming frameworks to stream 360-degree video data. Essentially, a video chunk is composed of many frames, and each video frame is divided into smaller grids. We create a video tile by concatenating the grids from the same location from all of these frames. And note that the user's field of view will only overlap with a few tiles. More importantly, we can encode and decode those tiles independently. For example, we can encode those tiles with different bit rates. Next, I would like to introduce a measurement study we did to identify the limitations of existing approaches. We mainly consider three approaches. The first one is YouTube, which streams the 360 video as a single tile, which is essentially same as regular videos. The second one is FOV only, which only streams the tiles which are visible in the field of view. The third one is FOV plus, which streams both visible tiles and some extra tiles surrounding the field of view. The way to determine what extra tiles to send is based on the estimation of head movement prediction error. Intuitively, if the prediction error is large, then we tend to send more extra tiles. By comparing the existing approaches, I want to explain the design space of 360-degree video streaming algorithms. Basically, YouTube can achieve high video quality because of sending the entire video. However, the other approaches have very low video quality because you only send a portion of the video. Compared with the YouTube approach, FOV only and FOV plus can speed up the decoding and save bandwidth as well. So the optimal solution in this design space is expected to achieve high video quality, fast decoding speed, and save bandwidth as well. So next, I will introduce the main results in our measurement study. So at first, let's take a look at the time of decoding entire 360 video frames. In our experiments, we mainly compared the YouTube approach and the naive tile-based approach. In the naive approach, we divide the video into 4 tiles and using 4 threads to decode them in parallel. In our experiments, we test both 8K videos and 4K videos. As we can see from this figure, the decoding time of each 8K video chunk is higher than 1.3 seconds for both approaches. Note that the chunk size of the video is only 1 second. If the decoding time is larger than the chunk length, then the user will suffer rebuffering. From this experiment, we can see that for 8K videos, decoding all the tiles is not fast enough on smartphones. Sending the entire frame wastes lots of bandwidth since the user only views a portion of the video. So only sending the visible tiles is one option to reduce bandwidth wastage. By only sending visible tiles, this figure shows the bandwidth savings for FOV only and FOV plus approaches compared with the YouTube approach. Across 10 head movement traces, we can find that the bandwidth savings can be as large as 80%. So therefore, it is possible to save substantial bandwidth by selectively sending tiles. So because of the head movement prediction error, the user may see some portion of the field of view in blank because we don't send all the tiles. The left figure shows the CDF of the head movement prediction error. We can see that there around 20% of time, you have even more than 50 degrees prediction error along the x-axis. For y-axis, the prediction error is smaller because the user has less movement along that axis. So this figure shows that we cannot avoid having a large head movement prediction error because the user's movement is not that predictable. So the red figure shows the received video quality across the FOV only and FOV plus approaches. We can see that these two approaches has much lower video quality compared with the YouTube approach. So that demonstrates that head movement prediction error can degrade the user, can degrade the quality of the received video. So from our measurement study, I would like to summarize what properties we expect from our design. So the first property would be the robustness to the head movement prediction error. So to realize that, we designed a novel layered video encoding framework. The second property is bandwidth saving and fast decoding speed. So we developed a layer adaptation algorithm to realize that. To go through the details of our design, a few design questions are listed here. So each component of our design is supposed to answer some questions here. So at first, let's discuss how we designed the layered video encoding framework. One major motivation of designing a new encoding framework is the limited resource on the smartphone. So for Android device, we find that only 4 concurrent hardware decoders can be run in parallel. So that limits the speed of decoding video tiles. So to handle that limitation, there are a few possible approaches you can use. The first approach is you can create many tiles, and you can allocate 1 tile to each thread. So for example, you have 16 tiles in total, and you can allocate 4 tiles to each decoder so that each decoder will have to decode 4 tiles sequentially. Note that in our experiments, we found sequentially decoding tiles is slow, such that this approach cannot effectively speed up decoding many tiles. In our experiments, we found that decoding multiple tiles sequentially in a single decoder has more overhead than decoding a single tile which has a larger resolution. So therefore, we can think about the next approach. So we only divide the video into 4 tiles, and we still allocate each tile to 1 thread. So in this case, if the field of view overlaps with all of the tiles, then we'll have to send all of them. Note that sending all tiles will waste lots of bandwidth and also resulting low decoding speed. So in our layered encoding framework, we incorporate both spatial splitting and temporal splitting. So in spatial splitting, we divide the video into tiles, which is the same as the tile-based streaming framework discussed before. In temporal splitting, we generate temporal layers for the frames in each tile as follows. So let's say we want to create 4 layers for a 16 frames chunk. So we divide those frames into groups, each of which has 4 frames. The first frame of each group will be assigned to the first layer, such that the first layer will have frames 1, 5, 9, and 13. The second frame of each group will be assigned to the second layer, so on and so forth for the other layers. The main benefit of this framework is that we can control the number of layers for different tiles. For example, in this figure, the dashed box highlights the field of view. So in the field of view, we can send all the layers to guarantee the received video quality. However, we can send only one layer for the other tiles. By not sending all the layers for all the tiles, we can speed up the decoding and save bandwidth as well. And next, we will look into how we optimize the transmission of the layers. At first, I will introduce the optimization algorithm we use. So we follow the model predictive control optimization framework, which optimizes the QoE for a time window. The input of this optimization problem includes the predicted throughput, the field of view, and also the buffer size. It outputs the bit rate of each tile and the number of layers from each tile. So it mainly aims to maximize the sum of the chunk QoEs in the current time horizon. So note that we also added a few efficiency constraints to reduce the complexity to solve that optimization problem. For more details, please refer to our paper. Next, now I want to look at what the objective function looks like. So we have seen that the objective is basically maximizing the sum of the QoE for the chunks in the current time horizon. So we follow the standard way of defining chunk QoEs, which is determined by a few factors, including quality changes, and rebuffering. So we take the weighted sum of these factors. So note that the quality indicates the quality of the field of view, and quality changes means the quality fluctuation across continuous chunks. So rebuffering is obviously captures the playback stall time. So note that because decoding time is non-trivial in this case, so we model the rebuffering time as a function of the throughput and decoding time. Next, I would like to introduce how we model the decoding time. So we model chunk decoding time as a function of the tile configuration, so which is basically a tuple indicating the number of tiles we want to download from the layer 2, 3, and 4. So in our system, we send all the tiles from the layer 1. So we model this function by using extensive measurement. Now I would like to introduce the implementation of our system. So our approach, Rubiks, is implemented as an Android app. Those dark boxes indicates the modules we just discussed. So here is the information about how we implement a decoder and the encoder and the video player on the smartphone. So now here is the details of how we set up our evaluation experiments. So we tested both 4K and 8K videos downloaded from the YouTube website. We mainly run our experiments on the recent smartphones like Samsung S7 and Mate 9. So for more details of the experiment settings, please refer to our paper. So now let's look at the overall performance of our system compared with the baselines we just discussed. So this figure shows that our approach has at least 14% improvement compared with the other approaches. For 8K videos, we can see at least 20% improvement in QoE compared with other baseline approaches. So next, note that from these two figures, we can see that our system Rubiks can achieve the best video QoE compared with other approaches. Next, I will explain why we can achieve the best video QoE. And also, I want to mention that based on the following results, I also want to explain whether Rubiks indeed has those properties we just discussed before. So the figure on the left-hand side shows that the bandwidth savings compared with the YouTube approach. We can see that our system Rubiks can have around 35% bandwidth savings, which indicates that layer adaptation indeed improves the bandwidth savings. In terms of video quality, we can see that our approach achieves very close video quality compared with the YouTube approach. Note that the YouTube approach was send the entire video, the entire video frame. However, for the FOV plus and FOV only approaches, both of them have very low video quality. So from these results, we can see that the layering helps save bandwidth without sacrificing the video quality. Next, let's look at the decoding speed. So the left figure shows the rebuffering time from various algorithms for 4K videos. We can see that our approach has lower rebuffering time than the YouTube approach, which sends the entire video frame. For 8K videos, slow decoding dominates the rebuffering time for 8K videos. So, and from this figure, we can see that our system Rubiks reduces the rebuffering time significantly because we have much faster decoding speed. So from this, we can see that selectively sending layers indeed reduces the decoding time. We also did a user study involving 30 users. In our experiment, we asked the users to rate the video quality in the range from 1 to 5. 1 indicates the worst quality, while 5 means the best. The bar plot illustrates the user ratings for different algorithms. We can see that Rubiks achieves the highest rating. So the reason of that is our system Rubiks has faster decoding speed, and also it is robust to head movement prediction error. So before I conclude my talk, I would like to introduce the related work. So there have been many works trying to propose to use tile-based streaming framework to stream 360-degree videos. But they still suffer from slow decoding speed and also low video quality because of the head movement prediction error. And there are also some proposals for video encoding schemes. For example, ROI-based encoding is one of them. So essentially, you can encode the user's region of interest with higher bitrate. However, this is not applicable to 360-degree videos because users' head movement is not predictable. And scalable video coding is another option. However, it is not supported on the current Android smartphones. Now, I would like to conclude my talk. So in our work, we did a measurement study to identify the limitations of the existing approaches. We proposed a novel layered video encoding framework, and we also implemented our system Rubiks on Android phones, and the results shows the effectiveness of our system. By moving forward, we plan to investigate how to design live 360 video streaming services, and also how to improve the energy efficiency of 360-degree video streaming services. Now, thanks, and I'm happy to take any questions.